tried to take a cautious, calculated baby step into the solar system, and the universe essentially just slammed the door on our fingers.
It really did. I mean, it was a harsh rejection of our entirely incremental mindset.
Right. Because for years, the absolute crown jewel of deep space exploration was supposed to be orbital fission. We were going to put these traditional, highly shielded nuclear reactors on rockets.
Which, on paper, felt like the logical next step.
Yeah, it was incremental, it was safe. We engineered these absurd, paranoid safety nets. I mean, literally installing physical poison wires made of neutron-absorbing materials.
Like cadmium and boron, right?
Exactly. Jamming them directly into the reactor cores.
Yeah.
The engineering logic was just that you needed this physical, mechanical lock to guarantee that absolutely nothing could trigger a chain reaction while the rocket was just sitting there on the launch pad.
Because we desperately wanted the thermodynamic efficiency of nuclear heating, but we were absolutely terrified of the isotopic footprint.
We wanted to ride a controlled atomic bomb into orbit, essentially, but only if we could keep it on a tight leash.
Right, because if a chemical rocket explodes on the pad, you have a massive fireball, sure. But it is fundamentally a local chemical tragedy.
Just a really big, expensive fire.
Exactly. But if a rocket carrying a live, critical fission reactor explodes in the lower atmosphere, you have a radiological event that suddenly crosses international borders.
Which is a geopolitical nightmare.
It's an uninsurable risk. So the plan was always to keep the reactor completely dead, completely inert, until it was circling in a highly stable, high-altitude parking orbit.
Like an orbit so high that it would take, at least 3 centuries for the spacecraft's trajectory to naturally decay?
Yeah, at least. Dragging it back into the atmosphere only after all the dangerous, volatile radioactive isotopes had just, naturally decayed into safe, quiet background radiation.
Right. It was this massive, multi-billion-dollar compromise with gravity and radiation, and then abruptly, that entire paradigm was just executed, terminated.
Completely wiped off the board.
But you are not looking at some boring, bureaucratic budget cut right now. You are looking at a stack of freshly declassified feeling engineering specs, physics white papers, and biological analyses that we have laid out on the table today.
It's a completely different map of the future.
It really is. Our mission right now is to pull back the curtain on what is actually replacing that canceled program. Because when the door was slammed on cautious orbital fission, it acted as a cosmic forcing function.
We couldn't tiptoe anymore.
Exactly.
Yeah.
Humanity is being forced to leap straight into something terrifyingly radical. We are looking at a hidden, unified blueprint of reality where cutting-edge, incredibly violent physics is colliding directly with raw biological wetware.
And the cancellation of those traditional space fission programs wasn't just a failure of funding or even a sudden loss of political nerve. It was a harsh realization of the sheer tyranny of the rocket equation.
The mass fraction limits.
Right. In orbital mechanics, everything is dictated by mass fraction limits.
I want to make sure we are completely clear on this because it is literally the wall that human engineering has been bashing its head against for 70 years. What exactly is this mass fraction limit forcing us to do?
So the mass fraction is just the ratio of your fuel weight to your payload weight. To move heavy payloads or fragile human biology, which is even heavier across the solar system, you have to move incredibly fast.
Because space is highly radioactive and is trying to kill you.
Precisely. You have to minimize transit time to avoid lethal compounding doses of galactic cosmic radiation. But to go that fast, you need a high specific impulse, which is essentially just a measure of engine efficiency.
And chemical rockets just physically cannot provide that efficiency, right?
No, they can't. The energy density of combusting hydrogen and oxygen is simply too low. So to go faster, you need more fuel.
But fuel has mass.
Exactly. So now you need to burn even more fuel just to push the unbound fuel that you are carrying.
It's just this brutal compounding penalty. The faster you want to go, the more the ship becomes just a giant flying fuel tank.
You eventually reach a point where the ship is like 99% fuel and 1% payload. That is the mass fraction limit. Fission was supposed to be the logical way out because uranium is millions of times more energy dense than chemical propellants.
But the capital expenditure, the highly specialized supply chains for enriched uranium,
and the insurmountable regulatory friction of putting fissile material on top of thousands of tons of explosive chemical thrust. It just became an impossible bottleneck.
The universe demands high energy, but our geopolitical and logistical realities down here just cannot tolerate orbital nuclear risks.
So we are forced to separate the two. We are entirely offloading the power plant from the spacecraft.
Which brings us to the beamed energy paradigm. And this is where things get genuinely insane. If we can't put the nuclear reactor on the ship, we leave the reactor on Earth, and we literally shoot the ship with the energy.
It sounds like science fiction, but the physics are completely sound.
I mean, the sheer madness of this alternative is hard to overstate. We are talking about building a massive 10-meter phased array laser system on the ground.
Right, and it's important to understand this isn't just one big, solid sheet of glass.
It's a synchronized grid, right? Thousands of individual emitters operating at a continuous output of 100 megawatts, firing directly upward, tracking a spacecraft moving at orbital velocities.
Yes.
But wait, wouldn't pumping that much concentrated energy straight up through the atmosphere, wouldn't it just boil the air? Doesn't the sky just become a wall of plasma that scatters the beam before it even reaches the stratosphere?
It absolutely does. And this is one of the most brutal optical nightmares in modern physics. When you pump 100 megawatts of coherent photonic energy through atmospheric gases, you induce this phenomenon called thermal blooming.
Thermal blooming, okay.
The laser physically heats the air molecules right in its path. And as the air heats up, its density changes, which alters the refractive index of the atmosphere.
So the air itself becomes a lens.
Exactly. The laser beam effectively creates its own diverging lens out of thin air. It defocuses and completely destroys its own coherence.
So how do you push a 100-megawatt column of fire through a chaotic medium that is actively, aggressively trying to disperse it?
You have to outsmart the atmosphere in real time. We are using adaptive optics. We are basically borrowing and weaponizing techniques that were originally developed for ground-based astronomy.
Like how they fix the twinkling of stars.
Right. Starlight twinkles because the atmosphere bends the incoming light. Astronomers use these incredible deformable mirrors that change shape thousands of times a second to cancel out that twinkle, creating a perfectly sharp image. But here we are reversing the entire process.
So instead of receiving a distorted image and trying to fix it, we are analyzing the atmosphere, calculating exactly how the air is going to bend our laser, and then deliberately firing a broken or pre-distorted beam.
Precisely. The phased array fires a wavefront that is mathematically inverted to the atmospheric turbulence sitting right above it. The atmosphere bends the light, sure, but because we pre-calculated the distortion, the air accidentally bends our broken beam back into a perfectly coherent, deadly precise needle of pure energy by the time it hits the vacuum of space.
That is just brilliant and terrifying. And the target receiving this energy is equally extreme, right? Because we offloaded the power plant, the spacecraft no longer carries its own primary energy generation. It acts entirely as a thermal receptacle.
It's completely passive in terms of generation.
It's a cosmic drag racer. That's the only way to describe it. The ship deploys this massive inflatable cislunar reflector, and it catches that perfectly corrected 1-micron wavelength beam of pure light.
And that reflector acts like a giant, blindingly hot steam kettle.
Right. It focuses all that trapped laser energy into a highly specialized heating chamber filled with liquid hydrogen propellant. And we're talking about heating that hydrogen to a blistering 10,000 Kelvin.
It flashes instantly from a cryogenic liquid into an ultra-hot plasma.
And this is where the drag racer analogy really locks in, because the spacecraft must absorb the entirety of its propulsive kinetic energy in a single, violently intense 1-hour burn window.
It has absolutely no choice. It only has access to that laser beam while it is in the direct near-field line of sight from the terrestrial ray.
Because the Earth is rotating.
Exactly. As the Earth rotates and the ship accelerates away, that window closes incredibly rapidly. During that single hour, the explosive expansion of that 10,000-degree hydrogen plasma is just funneled out the back through a magnetic nozzle.
Which generates a specific impulse of 3,000 seconds.
Which is astronomical.
I mean, to put that in perspective for you, the absolute best chemical rockets humanity has ever built max out around 450 seconds. This beamed thermal system generates so much thrust so quickly that it hurls the payload toward Mars on a trajectory that takes just 45 days.
Just a month and a half.
45 days? That completely solves the zero-gravity bone density loss problem. It solves the life-threatening cosmic radiation exposure. It solves the psychological horror of being trapped in a tin can for 9 months.
It completely rewrites the biological parameters of the mission.
But here's the most jarring part of the whole architecture. The ship itself doesn't even go all the way to Mars. The propulsion bus, this insanely expensive architecture with the inflatable reflector and the plasma heating chamber, it doesn't make the trip.
It can't. The economics of this infrastructure completely prohibit throwing away the propulsion bus. It is simply too valuable.
So what does it do?
Once the payload, the actual crew module, is accelerated to its massive transit velocity, the propulsion bus physically detaches. It then executes a highly calculated secondary maneuver known as a burnback.
A burn back.
Yes. It utilizes the very last remnants of its hydrogen propellant, and it catches the absolute fading edge of that terrestrial laser beam to violently alter its own trajectory. It bleeds off its escape velocity, specifically to remain securely trapped in Earth orbit.
Just slamming on the brakes so it doesn't leave the gravity well.
Exactly. It is left there, entirely empty, waiting for an immediate refueling of hydrogen so it can latch onto the next payload and ride that 100-megawatt beam all over again.
Meanwhile, the actual crew module is just hurling through the dark void. It has no main engine anymore. It's essentially an interplanetary cannonball.
A very fast cannonball.
And when it gets to Mars 45 days later, it doesn't have the massive propulsion system required to slow down, so it has to execute an extreme aero capture maneuver.
Right, because it hits the Martian atmosphere at pure interplanetary velocity.
It doesn't just use atmospheric friction to slow down, it uses extreme fluid dynamics. It hits the atmosphere so fast that the alien air physically cannot get out of the way.
It compresses the gas in front of the heat shield so violently that the compression itself superheats the air into a plasma.
It acts like a reverse rocket thruster made entirely of compressed alien atmosphere, just pushing back against the ship to break it into orbit. It's absolutely terrifying.
The thermal tolerances are beyond anything we've ever flown.
But, it forces a broader question. If we are completely throwing out the rulebook here and dealing with this level of extreme violent physics just to solve the mass fraction problem, why lasers?
That's the natural next question, yes.
Right. Why aren't we going straight to the ultimate, undisputed energy source in the universe? Why aren't we just using pure antimatter?
It is the absolute logical extreme of the mass fraction question. Matter-antimatter annihilation represents the physical upper limit of energy density, period.
Because it converts mass to energy with exactly 100% efficiency.
Exactly, as dictated by Einstein's equivalence principle. But the physics of pure antimatter propulsion introduce a relativistic nightmare that we physically cannot survive.
Let's break that down. Let's start with the simplest, most intuitive form of antimatter, electron-positron annihilation.
Right.
Because a positron is just the antimatter twin of an electron, right? Same mass, but a positive charge.
Correct. But if you mix a tank of electrons with a tank of positrons, their entire mass is converted into something incredibly lethal. Highly penetrating neutral gamma-ray photons.
And you can't build a rocket nozzle out of a magnetic field if the exhaust doesn't have an electrical charge. Gamma rays don't care about your magnetic fields. They just blast straight through the ship, cooking the human crew instantly and melting the physical superstructure of the vessel.
Exactly. You generate infinite energy, essentially, but you cannot direct it to create thrust. It just radiates in a sphere of death.
Yeah.
So propulsion theorists looked at a heavier alternative, proton-antiproton annihilation.
Which is a much heavier, vastly more complex reaction.
A hadronic reaction, yes. When a proton and an antiproton annihilate, they don't just instantly flash into gamma rays. The sheer mass of the particles creates a cascade of new particles called pions.
Pions.
Yes. Approximately 60% of the reaction energy goes into forming charged pions. These charged particles travel at roughly 94% the speed of light.
Wait, if we get 94% of the speed of light from charged pions, and because they have a charge, we actually can catch them with an advanced electromagnetic nozzle to generate thrust, why aren't we building this tomorrow? Where is the friction?
The friction is entirely contained in the other 40% of the reaction. While 60% of the energy creates charged pions, the remaining 40% goes into neutral pions. And neutral pions are incredibly violently unstable. They decay in roughly 10 to the negative 16 seconds.
That is a fraction of a nanosecond.
They don't even exist long enough to look at them. Before they even clear the magnetic engine well of the spacecraft, they decay into extremely hard, high-energy gamma rays.
And we are right back to the radiation problem.
Worse than before, honestly. The sheer volume of dense radiation shielding required to protect a human crew from that specific secondary gamma ray decay would have to be so incredibly massive, we're talking walls of lead and tungsten meters thick, that it entirely negates the weight advantage of using antimatter in the first place.
Your mass fraction is ruined all over again by the shield.
Completely ruined.
Not to mention the sheer impossibility of keeping a tank of antiprotons sitting around in the first place. You can't just put them in a metal bottle. If an antiproton touches the normal matter of the container wall, it annihilates.
Right, so you have to suspend them in a complete vacuum using a magnetic field.
But because antiprotons all share a negative charge, They violently repel each other. Even trying to store a single gram of pure antiprotons would generate an electrostatic pressure so immense it would instantly shatter any magnetic confinement field human engineering knows how to build.
Which is precisely why the beamed energy paradigm is the only survivable bridge to the deep solar system right now.
It's the only way.
Yes. By leaving the power generation firmly on Earth, we bypass the mass fractional limits, we bypass the electrostatic limits of antimatter storage, and we completely bypass the catastrophic radiation burden on the crew.
The spacecraft becomes incredibly light, mechanically simple, and ferociously fast. But to make this architecture a reality, we haven't actually eliminated the engineering bottleneck. We have just fundamentally shifted its location.
That's the reality of it. The bottleneck is no longer in the vacuum of space.
The bottleneck is right here under our feet. Because to fire a 100-megawatt laser array continuously into the sky, you need a terrestrial electrical grid capable of godlike, sustained power generation.
You can't just plug a 10-meter phased array orbital laser into the local natural gas plant.
No, you definitely cannot. And that brings us silently down from the sky and into the terrestrial war for commercial fusion. And the physics happening in these experimental reactor halls down here is just as intense and arguably more dangerous than what is happening in orbit.
The transition of magnetic confinement fusion from theoretical academic laboratories to actual utility scale, commercial engineering is entirely dependent on one highly specific material breakthrough.
Okay, let's get into the magnets.
Historically, to build the massive electromagnets required to contain the millions of degrees of fusion plasma, we used low-temperature superconductors. Materials like niobium-tin.
Right.
But those materials required cooling to near absolute zero using liquid helium, and their magnetic field strength had a hard physical ceiling. You simply couldn't push them any harder without them losing their superconductivity.
It would just fail.
Exactly. Now, the entire industry is pivoting to rare earth barium copper oxide, or REBCO, high-temperature superconducting tapes.
Let's clarify high temperature in this context, because we are still talking about extreme cryogenics. Right?
Absolutely. High temperature is a highly relative term in physics. We are talking about operating at intermediate cryogenic temperatures, roughly around 20 Kelvin.
Still unimaginably cold.
Yes. But the critical, world-changing advantage of REBCO isn't just that it operates at a slightly warmer temperature. It is the sheer magnetic field it can tolerate. These microscopic tapes can maintain their superconductivity in magnetic fields exceeding 100 Tesla.
100 Tesla.
And in the world of fusion plasma confinement, the math associated with magnetic fields is terrifyingly exponential. Fusion power density scales to the fourth power of the magnetic field strength.
Wait, I need to pause on that math, because that equation is the absolute key to unlocking this entire terrestrial power grid. Power scales to the fourth power of the magnetic field.
Right.
Meaning, if you can just double the strength of the magnetic field wrapping around your artificial star, you don't get double the power out of it. You get 2 times 2 times 2 times 2.
You get 16 times the power output from the exact same volume of plasma.
16 times the power. That is insane.
That single scaling law completely changes the architectural reality of energy generation. It means you no longer need to build these building-sized, multi-billion-dollar sprawling behemoths just to achieve a net positive energy gain.
You can shrink it.
By utilizing these 100 Tesla REBCO tapes, you can shrink a commercial fusion reactor down to the physical footprint of a large commercial truck.
It becomes this compact, violently intense machine.
Yes. But condensing that unfathomable amount of thermal and magnetic energy into a space that's small introduces an existential vulnerability, a vulnerability known in the industry as the quench.
The quench. It sounds like a catastrophic event from a sci-fi horror movie, and honestly, reading through the specs, the thermodynamic reality of it is horrific.
It's the nightmare scenario for any magnet engineer.
You have this incredibly dense magnetic field carrying an absurd city-powering amount of electrical current through these frozen superconducting tapes. And all it takes to trigger a quench is one tiny microscopic material flaw, right?
Just one. A single localized hotspot where the temperature ticks just a fraction of a degree too high, or where the current density becomes just slightly too clustered.
And what happens when that spot gets too hot?
When that incredibly localized spot exceeds its critical threshold, the physics flip instantaneously. It loses its superconductivity. It instantly becomes a normal, highly resistive piece of metal.
And that's bad because of the insulation, right?
Exactly. Now, in traditional magnet design for the past century, You wrap layers of organic insulation like epoxy or polyamide around the superconducting wires. This insulation ensures the electrical current only flows exactly where you want it to flow, in a continuous, highly controlled spiral.
Keeping it in its lane.
Right. But if a hot spot develops in an insulated magnet, that massive, unstoppable river of current hits the newly resistive wall of that hotspot. And because of the insulation trapping it in its lane, the current has absolutely nowhere else to go.
It is literally forced to push straight through the resistance. And pushing massive current through resistance generates extreme Joule heating.
It creates massive heat, which heats up the tape around it, which makes even more of the tape resistive, which generates even more heat. It's an immediate runaway thermal chain reaction. We are talking about a timeline of milliseconds here.
The localized temperature spikes so violently that the cryogenic liquid helium coolant violently boils and expands. The physical structure of the magnet fractures under the thermal stress, and the massive stored magnetic energy is dumped instantly into the machine as raw heat.
The billion-dollar machine literally vaporizes itself from the inside out.
Vaporized. To safely operate these highly compact, extreme field fusion reactors, the industry had to invent a mind-bending solution to the quench vulnerability. And the solution is utterly counterintuitive to everything we know about electrical engineering.
It really is a paradigm shift.
It'll completely remove the insulation.
Yes. It is a technique called no insulation winding.
They literally wind the bare superconducting tapes directly against one another, raw metal on raw metal, relying solely on the microscopic contact resistance between the turns of the tape.
Which sounds completely crazy.
Hang on, that defies the basic logic of insulation. If electricity can just jump the tracks and cross the bare metal whenever it wants, how is the entire magnet not constantly short-circuiting under normal operating conditions?
It all comes down to how electrical current chooses its path. Under normal, perfectly stable cryogenic conditions, the superconducting tape has absolute zero resistance.
Zero.
Right. The metal-to-metal contact between the layers, however, has a microscopic, non-zero amount of resistance.
Because it's not a perfect bond.
Exactly.
Yeah.
And electricity will always take the path of absolute zero resistance. So the current willingly spirals along the entire length of the tape, traveling thousands of meters around the magnet, completely ignoring the bare metal contact because traveling through the spiral path is perfectly frictionless.
But the moment a quench begins the exact nanosecond, a localized hotspot forms and generates a wall of electrical resistance. The entire dynamic changes.
Everything changes.
The current hits that microscopic wall, but because there is no organic insulation trapping it in that specific spiral path, the current can literally cross the gap.
It spontaneously bypasses the resistive hotspot. It flows radially outward across the bare metal into the adjacent, still superconducting layers of the tape.
It jumps the tracks to save itself. It dynamically reroutes its lifeblood to prevent its own destruction in real time.
It's an engineered reflex.
We are building terrestrial electrical grids that possess a central nervous system. It's the equivalent of touching a hot stove and your hand reflexively pulling back before your brain even registers the burn. The machine senses a breakdown in its own architecture and organically routes around the trauma.
Written directly into the laws of conductivity.
It's beautiful, honestly.
It transforms a catastrophic vaporizing failure into a temporary, entirely safe redistribution of electrical current. It allows these highly compact becomics to push the absolute physical limits of magnetic pressure without the constant looming threat of a vaporization event.
But solving the magnetic confinement is only half the battle of the energy grid. You have these brilliant self-protecting magnets, but they are starving.
They need fuel.
Right. To power the fusion grid, which in turn powers the 100-megawatt laser array, which ultimately pushes the orbital drag racer. We need fuel. And here is where we hit the existential fuel crisis that nobody is really talking about.
The tritium bottleneck.
The fusion reactors we were relying on run on a very specific atomic mixture, deuterium and tritium. Deuterium is incredibly easy to source. It is a heavy isotope of hydrogen, and you can literally distill an endless supply of it out of seawater.
We have oceans of it, literally.
But tritium is the silent bottleneck of human civilization right now. The entire global civilian inventory of tritium is estimated to be roughly 20 kilograms.
In the entire world.
20 kilograms to power the future of humanity.
Because tritium is a radioactive isotope of hydrogen, containing 1 proton and 2 neutrons. Its fatal flaw as a fuel source is its half-life of roughly 12 years.
So it's ticking away as we speak.
Exactly. It does not just sit around stably in nature. It constantly and aggressively decays away into helium. Currently, we only harvest it as a rare byproduct from a very specific aging fleet of heavy water fission reactors.
So a massive commercial fusion economy simply cannot rely on mining or purchasing tritium. To survive, these fusion grids are forced to adopt a biological paradigm. They must literally breed their own fuel to survive.
They must deploy what are called tritium breeding blankets.
How exactly does a machine made of supermagnets breed a radioactive isotope?
By using its own violent waste products. The walls of the fusion chamber are lined with incredibly thick baths of liquid lithium, or sometimes intricate beds filled with ceramic lithium orthosilicate pebbles.
Okay.
When the deuterium and tritium fuse inside the magnetic bottle, the reaction releases an unfathomable amount of high-energy neutrons.
And because neutrons have no electrical charge whatsoever, that incredibly powerful 100 Tesla magnetic field can't contain them. The magnets only hold the charged plasma.
Right. The neutrons fly straight out of the plasma, smash into the physical walls of the reactor, and plunge directly into that lithium blanket.
And when a high-energy neutron collides with a lithium atom in the blanket, it triggers a violent nuclear reaction.
Yes. Depending on the specific isotope of lithium, this collision is either endothermic, requiring kinetic energy from the neutron, or exothermic, releasing additional energy.
But the ultimate byproduct of both collisions is helium, and crucially, a completely fresh atom of tritium.
The reactor uses the lethal radiation it produces to actively mutate the walls of its own containment chamber into the exact fuel it needs to take its next breath.
It's an enforced, closed-loop life cycle. And the engineering target for these reactors is tritium breeding ratio above 1.05.
Which is a very tight margin.
Right, meaning for every one single tritium atom that is burned up in the plasma, the lithium blanket must successfully breed 1.05 new atoms, ensuring absolute self-sufficiency and a slight surplus to start new reactors.
Some advanced inertial confinement architectures, which use massive cascading waterfalls of liquid lithium to absorb the neutron impacts, are actually modeling breeding ratios as high as 1.8.
But this closed-loop system is highly precarious. If the breeding blankets fail to meet that strict ratio, or if the initial startup costs of turning on thousands of commercial reactors require more initial tritium than we physically possess on Earth,
the entire terrestrial energy grid collapses before it even begins.
Which is why we have to look away from the Earth. We have to look up. And that introduces the frantic, deeply silent rush currently underway to mine the lunar regolith. We are talking about the extraction of helium-3.
The lunar gold rush.
Helium-3 is a stable isotope of helium with 2 protons and 1 neutron. It is incredibly, vanishingly rare on Earth because our strong magnetic field and thick atmosphere act as a shield, deflecting the solar wind that carries it.
But the moon has no such magnetic shielding.
None. For billions of years, the solar wind has been relentlessly baking helium-3 directly into the lunar topsoil. Estimates suggest there are over 1 million tons of it trapped in the pulverized glass and dust of the lunar regolith.
It's just sitting there on the surface.
Why is helium-3 worth building an entirely new interplanetary supply chain?
Because helium-3 unlocks the holy grail of physics. Entirely aneutron fusion.
Electronic. Without neutrons.
Exactly. If you fuse an atom of helium-3 with an atom of deuterium, the resulting nuclear reaction does not produce those wild, destructive, high-energy neutrons. Instead, it produces highly energetic, positively charged protons.
And because they're charged, they can be controlled by magnets.
Exactly. Which means there is no massive radioactive wear and tear on the reactor walls. You no longer need the complex, dangerous liquid lithium breeding blankets.
And most profoundly, you don't have to boil water to turn a steam turbine to generate electricity. Because the reaction produces charged protons, you can capture their kinetic energy directly using electromagnetic fields, converting the fusion reaction into raw electricity with staggering efficiency. It sounds perfect in theory, but setting up this lunar supply chain exposes a critical vulnerability. We are talking about establishing an entirely new physical paradigm where our terrestrial power generation produces zero radioactive flux. But the supply chain for that power stretches 238,000 miles across the vacuum of space.
It's an unprecedented logistical vulnerability.
We are moving our most critical planetary infrastructure into the noisiest, most radiation-soaked environment imaginable. Classical communication and radar systems are completely blinded by cosmic static, solar flares, and atmospheric interference.
To protect and coordinate this new orbital grid, classical physics simply isn't enough anymore. We have to exploit quantum mechanics.
We're going quantum.
We have to. The physical infrastructure we are placing in orbit is rapidly evolving beyond mere transportation or resource logistics. We are deploying quantum technologies into the aerospace domain because terrestrial environments are just too noisy, too disruptive for the delicate states of quantum entanglement.
Take quantum cryptography and entanglement networking. Down here on Earth, we try to send entangled photons through fiber optic cables to create perfectly secure, unhackable communications.
Right.
But the physical glass in the fiber isn't perfect. It absorbs photons. The delicate quantum state suffers from exponential decay as it travels through the glass, physically constraining any quantum network to a few hundred kilometers before the signal literally dies.
So the solution is to remove the glass entirely. We are moving the quantum networks to the vacuum of space.
We are taking entangled photons, particles whose quantum states are instantly linked regardless of the physical distance separating them, and we are firing them from ground stations on Earth straight up through the atmosphere to orbital satellites hurtling by at 20,000 kilometers per hour.
And we are successfully executing what is known as entanglement swapping in microgravity.
Entanglement swapping, how does that even work?
It relies on the deeply unintuitive principles of quantum teleportation. You begin with two completely independently entangled pairs of particles. Let's call them pair A and pair B.
Okay, two separate pairs.
By performing a very specific joint measurement, a Bell state measurement on one particle from pair A or one particle from pair B, you force the remaining two particles to suddenly become entangled with each other.
Wait, so these two remaining particles have never interacted, they have never physically touched?
Never. And they may be thousands of kilometers apart. Yet they instantly share a quantum state. By executing this operation on orbital nodes, we completely bypass terrestrial decoherence. We are actively building the scaffolding for a planetary, unhackable quantum internet.
But the entanglement isn't just being used for secure communication. It is actively being weaponized into something deeply unsettling: quantum radar.
This is where stealth completely breaks down.
Right, because modern stealth technology is entirely based on geometry and radar-absorbent materials. You try to bounce a classical radio wave off a stealth fighter, and the sharp angles of the plane's geometry deflects the wave away, or the specialized skin of the aircraft absorbs the electromagnetic energy, returning nothing but background static to your radar dish.
You are effectively blind.
But quantum radar breaks that classical dynamic entirely.
Quantum radar operates on a radically different principle called quantum illumination.
Quantum illumination?
Instead of broadcasting a massive, incredibly loud wave of classical electromagnetic energy and hoping for a faint echo to return, the quantum radar system generates pairs of entangled photons.
Okay.
One photon, the idler, is kept completely isolated, safely contained inside the radar facility. Its entangled twin, the signal photon, is broadcast out into the open environment.
It's like having a flashlight where every single photon of light leaving the bulb has a psychic twin sitting safely in your pocket.
That's a great way to visualize it.
You shine that flashlight into the dark, and if an adversary out there tries to shine a fake flashlight back at you to spoof your sensors, or deploys dense active electronic jamming to confuse you with a massive wall of white noise, you don't even look at the noise. You just check the psychic twins in your pocket.
That is the exact mechanism. When your signal photon bounces off a stealth target and eventually returns to your detector, it is buried in an overwhelming, blinding amount of environmental noise and active jamming. A classical radar would be completely useless.
It would just see static.
But the quantum system measures every single returning particle of light against the isolated idler photons you kept in the facility. Because the quantum correlation, the entanglement, persists even at incredibly low signal-to-noise ratios, the system can instantly discard any photon that does not possess that distinct matching quantum signature.
It filters out the noise.
With over 90% accuracy.
The concept of stealth is suddenly totally obsolete. You cannot hide from a sensor that checks the fundamental quantum ID of the light bouncing off your hull. Active jamming, stealth geometry, atmospheric clutter, they become mathematically irrelevant. The quantum radar extracts the genuine, undeniable silhouette of the target directly from the static.
It's a complete paradigm shift in situational awareness.
But that is just looking at things inside our local atmosphere. When we take these incredibly sensitive quantum sensors and point them at the macrocosmos, the deep universe, our entire rigid understanding of reality shatters again.
We are seeing this disruption most clearly in the deployment of atom interferometers.
Atom interferometers.
Right. Classical optical interferometers, like the famous facilities used to detect gravitational waves, use lasers bouncing between massive physical mirrors to measure microscopic changes in distance caused by passing ripples in space-time.
Right, bouncing light off massive objects.
But atom interferometers completely invert the roles of light and matter. Instead of using a physical object to measure a wave of light, they use light to measure the fundamental nature of matter. Specifically, they utilize ultra-cold isotopes, like strontium atoms, cooled to mere fractions of a degree above absolute zero.
At temperatures that extreme, the thermal kinetic energy of the atom is almost completely removed. The atoms stop behaving like solid little billiard balls bouncing around. The extreme cold forces them to behave purely as quantum waves.
Correct. The instrument then uses highly precise laser pulses to physically split the quantum wave function of the strontium atom.
Splitting the atom, but not in the explosive sense.
Right, splitting its probability. It sends the single atom into a literal state of superposition, where it travels down two separate physical paths simultaneously. Further laser pulses are then used to recombine the wave function back into a single state.
And by measuring the complex interference pattern created when the two halves of the atom's existence merge back together, we can detect incredibly faint anomalous forces.
We can observe ultralight scalar dark matter interacting with the fine structure constant of the atom.
We are no longer just looking at the universe through the electromagnetic spectrum. We are sensing the structural deformations of the void itself. And what these sensors are telling us is that the void is far more fluid and violent than we ever suspected.
It's not empty at all.
Let's look at the recent observation of a superluminous supernova from 10 billion years ago. We pointed our lenses at an explosion that happened closer to the Big Bang than to today. And because of gravitational lensing, where the sheer mass of an entire galaxy physically bends the light of the explosion around it like a magnifying glass, we didn't just see a static flash of light.
We saw a distinct chirp.
A periodic, rhythmic modulation in the light.
That chirp is the observable physical manifestation of lens-thirring precession.
Lens-thirring precession, okay, which is more commonly known in physics as what?
Frame dragging. General relativity predicts that a massive object doesn't just rest in the fabric of space-time like a bowling ball on a mattress. If that massive object is spinning rapidly, the extreme gravity literally drags the fabric of space-time around with it, like a spoon stirring thick, viscous honey.
What we observed in that ancient lensed supernova was the exact moment of birth of a magnetar.
Yes.
A magnetar is an ultra-dense neutron star spinning wildly out of control, generating magnetic fields of 10 to the 15 Gauss.
Which is a number that's hard to even conceptualize.
To ground that number for you, a standard refrigerator magnet is about 100 Gauss. We are talking about a magnetic engine so intense that if it were located halfway to our moon, it would instantly wipe the magnetic strip on every single credit card on planet Earth and pull the iron directly out of your bloodstream.
And that rapidly spinning, unimaginable magnetic engine is dragging space-time so violently that it causes its own surrounding accretion disk of plasma and debris to wobble rhythmically.
That wobble physically obscures the explosive light of the supernova in a rapid, pulsating pattern, creating that distinct chirp.
Observing this confirmed a monumental shift in cosmology.
The universe isn't just expanding outward like a rigid balloon. It is expanding via a fluid, dynamic pressure. Space-time itself can be churned, twisted, and dragged by local extremes of mass and electromagnetism.
It's a dynamic fluid.
It makes you realize how fragile our classical perception really is. We are shooting entangled psychic trends out of radar dishes to defeat stealth, and we are measuring the fluid drag of space-time 10 billion years in the past, using atoms cooled to absolute zero.
But there's another layer to this.
Right. Here is where we reach the ultimate twist of this entire blueprint. We have laid out this incredible infrastructure. We have solved the transit bottleneck with 100 megawatt laser drag racers. We have solved the energy bottleneck with self-protecting, no insulation fusion grids. We have rewritten cosmic perception with quantum sensors.
But the ultimate bottleneck to deep space isn't the engineering.
It isn't the physics. The bottleneck is us.
The transition from mechanical infrastructure to biological reality. is the most unsettling synthesis of modern aerospace engineering.
Unsettling is the word for it.
As our spacecraft become increasingly autonomous, traveling distances where light-speed communication delays make remote human piloting absolutely impossible, they require immense onboard artificial intelligence to navigate the hazards of the solar system.
But advanced silicon-based AI possesses a severe, almost insurmountable power limit. To run a state-of-the-art predictive learning model requires megawatts of constant electrical power and massive, heavy thermal cooling systems to prevent the silicon from melting.
And every watt dedicated to computing is a watt stolen from life support, magnetic shielding, or propulsion.
So the ultimate takeaway here isn't just that we're building better rockets, it's that the universe demands efficiency. And when you push mechanical engineering to its absolute bleeding limits, whether it's self-healing electrical grids or massive silicon supercomputers, the only way to survive is to abandon the machine and embrace the biology.
The universe favors the organic.
Because you look at the biological human brain, and it is the most advanced, plastic, intuitive neural network in the known universe. And it runs on exactly 20 watts of power.
A fraction of a standard light bulb.
It doesn't need liquid nitrogen cooling. It needs a slow drip of glucose and oxygen.
This extreme energetic disparity has birthed the highly classified field of biological computing in aerospace. We are moving completely beyond theoretical silicon simulations. We are dealing with the reality of remote access wetware computers.
Wetware.
These are actual processing units that utilize living human brain cells, specifically neural midbrain organoids grown in vitro as their core computational substrate.
Wait, I need to pause here because you need to feel the weight of what we are talking about right now. Silicon is out. We are building the supercomputers of tomorrow out of living human brain cells floating in nutrient jars.
Yes.
And we aren't just doing this in sterile basement labs on Earth. We literally grew these organoids in orbit. We sent human brain tissue to the space station to see if it could calculate in the void.
The microgravity environment of the International Space Station provided an unprecedented, incredibly hostile proving ground. The biological substrates were subjected to the profound stress of microgravity and high ambient cosmic radiation.
And the results were profound.
The organoids didn't just survive the exposure, they demonstrated a terrifying degree of adaptive genetic plasticity. When the researchers subjected the wetware to hardware failures or deliberate fluctuations in their life support environments, the neural networks physically adapted.
They didn't crash like a computer program experiencing a bug. They rewired their own physical architecture.
Actively. They actively formed new synaptic connections and altered their own chemical signaling pathways to maintain computational coherence in an environment that should have destroyed them.
They adapted to catastrophic failure through sheer biological will. And now, the engineering specs suggest we are merging these living neural nets directly with quantum devices. We are trying to mimic perfect artificial photosynthesis, feeding quantum-entangled energy directly into a biological brain jar to power its calculations.
It is Frankenstein's monster, crossed with a quantum supercomputer.
It is the active crossbreeding of quantum mechanics with living tissue. But the fundamental vulnerability of biological wetware is that it ages. Cells degrade.
Epigenetic markers accumulate on the DNA over time, leading to cellular senescence, neurodegeneration, and eventual cellular death.
An autonomous interstellar mission lasting decades cannot rely on a biological computer that develops the equivalent of Alzheimer's disease halfway to Alpha Centauri.
Which introduces the final, most radical cellular hack in the blueprint: epigenetic reprogramming via the Yamanaka variants.
The Yamanaka factors, a cocktail of 4 specific proteins that can take a fully mature, aging adult cell and forcibly revert it back into a youthful, blank slate stem cell. It strips the age right out of the biology.
Historically, the profound danger of the Yamanaka factors, specifically the protein known as C-mica, was that while they successfully reversed aging, they were highly oncogenic.
Meaning they cause cancer.
Rampant, uncontrolled cancer in animal models. You would cure the aging, but the tissue would immediately form lethal tumors.
But advanced AI models, analyzing billions of biological permutations and genetic sequences, have autonomously mutated human genetics to refine this exact process. By deploying highly selective AI-generated Yamanaka variants, we can execute what is known as partial reprogramming.
Right, partial reprogram.
To explain partial reprogramming, imagine the DNA in the cell as the hardware and the epigenetic methylation as chemical rust that accumulates on top of it over time. The DNA is still perfectly intact, but the cell can't read the code anymore because the rust is blocking it.
The Yamanaka variants strip the rust away.
But they stop the reprogramming process just before the cell loses its functional identity and reverts into a stem cell. We make the brain cell perfectly young again, but it remains a functioning brain cell, completely bypassing the cancer risk.
The documented results of this AI-driven partial reprogramming show a staggering 50-fold increase in cellular age reversal. We are achieving an artificial, highly localized immortality within these biological substrates.
The organoids grown in orbit are no longer just fascinating experiments in human biology. They are the explicitly intended computational substrates for the next generation of interstellar ships.
They are highly efficient, genetically immortalized neural networks capable of massive parallel processing on just 20 watts of power.
So humanity isn't just building faster rockets or sharper telescopes. We are actively crossbreeding quantum entanglement, self-protecting 100 Tesla magnetic fusion grids that sense their own destruction, and living, thinking biological wetware.
It's a complete convergence of disciplines.
We aren't just exploring the future, we are violently rewriting what it means to be a biological species traveling through base reality. And it leaves you with this final, completely unanswerable question to mull over.
What's the question?
If an interstellar ship is powered by a self-protecting magnetic fusion grid that senses its own pain, and it's steered by a 20-watt biological human brain organoid that has been genetically reversed to never age, at what point does that ship stop being a vehicle and start being the next evolution of a living species? And more importantly, what happens when it wakes up?